Welcome and thank you for joining. In this lesson, we'll explore transformations of primary trigonometric functions. Our focus will be on translations. And for this, we're looking into two basic trigonometric functions, y equals sine of x and y equals cosine of x. The first translation we're looking into is the vertical translations. Now, great news. This is something that we have done in the past. So we have observed vertical translations in functions in Unit 3 in this course. And now we are applying the vertical translations to trigonometric functions. So for this, we have a number that is added to the function itself, to the y values of the function, y equals sine of x, or y equals cosine of x. So let's take a look at our first examples. So y equals sine of x plus 2 and y equals sine of x minus 1. So the graph you see here on the grid is the graph of the basic sine function, y equals sine of x. And on the same grid, we will be drawing the graphs of y equals sine x plus 2 and y equals sine of x minus 1. Now recall that whenever we draw graphs of trigonometric functions, we focus on the 5 important points, and these are the 3 x-intercepts for the sine function, the maximum and the minimum. So whenever we add a number to sine of x, or to y equals sine of x, means that the y values of this function are increased by 2 units. And for this, what we do is we visit every important point, each and every one of the 5 important points, and we change the y values, and only the y values, by adding a 2 to it. So they're increased by 2. The same input of x values will produce y values 2 units greater. So the point where x equals 0, y equals 0 will take us to the x equals 0, y equals 2. The next point, the maximum, has the y value of 1 increased by 2. That will make this equal to 3. Then we have the x-intercept, y equals 0 becomes y equals 2. Then the minimum of y equals negative 1 will go up by 2. And lastly, we have this x-intercept, which is at 360 degrees, y equals 0, and now it will become 2 units greater, 0 plus 2. Now that we have plotted the 5 important points for y equals sine x plus 2, we'll connect all the points with a smooth curve. Please be sure that you draw the graph curvy, okay, and not a straight line. Do not use a ruler to connect these points because this is not a linear relation, and we have discussed this already when we explored the graphs of basic trig functions. Next, we're looking into the function y equals sine of x minus 1. Now we get the idea. Again, we are looking at y equals sine of x, which is the basic function. And this time we are bringing the y values 1 unit lower. So because we're subtracting 1. So the x value of 0, y value of 0, for the same x value, we're going to have the y value 1 unit smaller. So that will take us to y equals negative 1. Next we have y equals 1. It will become 1 unit smaller. That's 0. Y equals 0 will become negative 1. Y equals negative 1 will become negative 2. And y equals 0 again will become negative 1. So again, we'll connect these points together. We'll connect these points together with a smooth curve. And here we go. This would be the graph of sine of x minus 1. Now, in a similar way, we're working with the graphs of cosine of x plus 2 and cosine of x minus 1. For the cosine curve, the basic cosine curve, which is the graph that you see right here, the 5 important points are at the 2 maximums, the 1 minimum, and the 2 x-intercepts. So each and every point will undergo this transformation, which suggests that every point will have the y value increased by 2 units. So let's get started with our first function, y equals cosine of x plus 2. And we're going to say that y equals 1 becomes a 3. Y equals 0 will become a 2, so 2 units greater. Negative 1 will become a 1, that's 2 units greater. Again, 0 will become 2 units greater, which is a 2. And lastly, this maximum of 1 will increase by 2 units, so that will take the maximum at y equals 2. We'll connect all the points with a nice smooth curve. And this will be the graph of the function y equals cosine of x plus 2. Next, we're going to do cosine of x minus 1. I encourage you to do this on your own. It's pretty straightforward. So y equals 1. We'll go 1 unit lower. So that will take us to y equals 0. And obviously x stays the same, 0. So y equals 0 becomes y negative 1. Y of negative 1 becomes negative 2. Y of 0 becomes negative 1. And then lastly, we have y of 1 that becomes 0. Now we'll connect the points again with a nice smooth curve. And there goes the graph of the function y equals cosine of x minus 1. Now, if we were to describe these transformations, then we would say that for sine of x plus 2 or cosine of x plus 2, the graph, the basic graph, has undergone the vertical translation. For short, we write vertical translation, VT, of 2 units up. And for sine of x minus 1 and cosine of x minus 1, we're going to say that the graph, the basic graph of sine or cosine, underwent the vertical translation of 1 unit down. So the next thing that we want to look at is how to determine the specific features of each graph. So how did the features of the graphs of sine and cosine functions change due to vertical translations? So when we talk about the features of trigonometric functions, we focus mainly on the axis of symmetry, the minimum, the maximum, the period length, but that is something that is not being discussed in this section of the lesson. So what I want to bring your attention to is axis of symmetry. Remember that for the sine function, the axis of symmetry is at y equals 0. And this would be the axis of symmetry, right? Y equals 0. And same for the cosine function, the axis of symmetry, which is the line that divides a graph into 2 equal halves, the upper and the lower half, which have the same height. So axis of symmetry, again, y equals 0. So when you look at the transformations, when we add a 2 to the function, then the axis of symmetry, as you can see, has moved from y equals 0 to y equals 2. And I'm just going to bring this one a little bit higher. You can see that the axis of symmetry has moved to y equals 2. And that is equal to the vertical translation. In a similar way, we can discuss the axis of symmetry for the second function, sine of x minus 1. So you see that the axis of symmetry has moved with the function, the sine of x minus 1, and it has been brought down to y equals negative 1. So in conclusion then, we're going to say that the equation of the axis of symmetry is going to be y equals c, or y equals the vertical translation. And that will happen for any trigonometric function. So for sine, cosine, and for tan. In a similar way, we can discuss the axis of symmetry for the cosine function. So we're going to say that the axis of symmetry for both functions will be at y equals the vertical translation, or y equals c. Now, the next thing that we want to discover or connect or analyze, I should say, is how to connect the maximum, the minimum, the equation of axis of symmetry together. Now, when you look at y equals sine of x plus 2, you see that the maximum value of the function is at y equals 3, and the minimum is at 1. So we're going to write that maximum is 3, minimum is 1, and the equation of the axis of symmetry, we said that it is at y equals 2. And here we go, y equals 2. Now, for the next function, the sine curve right here, we see that the maximum is 0, the minimum -2. And the equation of the axis of symmetry has been brought down to y equals -1, so right here. So we're going to say that the same thing happened for the cosine function. We use the same translations for both of them. The only thing that changed was the curve, sine or cosine. So the maximum was at 3, minimum at 1. Axis of symmetry was at y equals 2. And for the cos x minus 1, maximum was 0, minimum was -2. Then the equation of the axis of symmetry was at y equals -1. So in conclusion, we say that the equation of the axis of symmetry will always be at y equals c, right? As you can see here, axis of symmetry ended up being at c. And in order to determine the minimum or the maximum, I want us to go back to our graphs. And what we're going to do is look at the basic function first. So in the basic function, you see that the maximum is 1 unit higher than the axis of symmetry. So that gives us the amplitude of 1. Or the minimum is 1 unit lower than axis of symmetry. So that gives, again, the amplitude of 1. So whenever we measure the location of the maximum or minimum, we see how far from the axis of symmetry is the min or max. And the distance would be always equal to the amplitude. So no matter what kind of translation we have applied to. So the location of the axis of symmetry, though, will tell us how far the maximum goes. So in general, we're going to say that the maximum is going to be equal to wherever the axis of symmetry is, and then you add the amplitude. So this is the axis of symmetry at C. You add the amplitude, you hit the maximum. This is the axis of symmetry, right? So you subtract the amplitude, you hit the minimum. So I hope that this makes sense, and I'm going to write now the equation. So again, as we mentioned, for the maximum from the axis of symmetry, we go up by the amplitude of the function. Use the absolute value because sometimes the amplitude of a function can be connected to a negative value of a. And when we talk about amplitude, we talk about the length or the height of the graph, right? So half of the height of the graph. So it has to be a positive, in other words. For the minimum, we're going to say from axis of symmetry, we go down by the amplitude. And in general, we're going to say that the equation of the axis of symmetry of the C value is always going to be halfway the max or and the min, which makes this axis of symmetry the midpoint of max and min. So another way of interpreting axis of symmetry is the average of the min and max, which is max plus min divided by 2. So with this in mind, we're going to practice a couple of questions when we're given the equations, and then we'll have to figure out what the minimum, maximum, and the equation of the axis of symmetry is. So we learned that the axis of symmetry is easy to identify by simply looking at the number that's been added to the function or subtracted to the function, right? So addition and subtraction, same thing. So you have added a -3, or you can say we subtract a -3. So y equals -3 will be the value, the equation of the axis of symmetry. So let's write that down. And in the next equation, y equals 1 would be the equation of the axis of symmetry because it's exactly this number, so y equals this exact same number. Now, when we talk about the min and the max, we need to know what the amplitude of the function is. The amplitude of the function in the first example is the absolute value of 2, and that would be equal to 2. Now, in the next example, the amplitude of this function will be the absolute value of -3. That makes the amplitude equal to 3. So whenever we find the minimum value of a function, we go from the axis of symmetry and we subtract the amplitude. So from the axis of symmetry, subtract the amplitude. So what that means is that in our case, axis of symmetry at -3, subtract the amplitude, which is +2, will give us a value of a minimum of -5. So we'll say that the value of the minimum of this function will be -5. Now for the next function, we have the value of c equal to +1. That's our c value. And now we are subtracting the amplitude, which is 3, +3, right? And that will take the minimum of the function at y equals -2. So we say that the minimum is -2. Now, in a similar way, we reason about the maximum value of this function, but for the maximum, as we know, we go the axis of symmetry, which is c, and now we add the amplitude. So c, and then plus the amplitude. And now all we have to do is substitute. Here we have a c value of -3, and here we have a c value of 1. Now the amplitude for the first function is equal to +2, so we add 2. And the amplitude of the second function is +3. Remember, amplitude positive. So that will make the maximum value of this function equal to -3 plus 2, that is -1. And the maximum value of this function will be 1 plus 3, which will make this equal to +4. And this is how we find the minimum or the maximum, by using the equation of the axis of symmetry and the amplitude of a function. Okay? Now, if we want to find the min or the max without having to graph the function, then we're going to say for the minimum, we're going to go from the axis of symmetry and we'll subtract the amplitude. And for the maximum, we're going to go from the axis of symmetry and we will this time add the amplitude. So what we were explaining before. So in the next example, we have to draw the graph of a sine function where we know the min and we know the max, we know the period length, and then we have to find the equation of the graph. So since we're trying to draw the equation of a sine function, so we're going to write y equals sine of x. So it's being transformed to have a minimum. Now remember that for sine of x, the minimum is -1 and the maximum is +1. So what that means is that since we have different values for min and max, it means that this function has undergone vertical expansions. It looks like the min and max are not just 2 units apart from each other, like in the basic function. So therefore, we're going to have to find the amplitude. So we're going to say that the equation we're looking at is y equals a and then sine of x. Now, obviously, in this case, you see that we also might have had a vertical translation. Why? When there are no vertical translations, when you are stretching the graph of a function, the minimum and the maximum will be at opposite values or will have opposite values. And in our case, we don't have opposite values, but we have, numbers that are both positive as a matter of fact. So what that means is that we must have had a vertical translation as well. So what I would do is I would start off with finding the value of c. I know that the value of c will be halfway the min and the max, or the average of min and max. So we're going to say c equals maximum plus minimum divided by 2. So the value of c would be equal to maximum of 7, minimum of 1 divided by 2, which is 8/2, and it will give the c value of 4. So the equation of our function now is y equals a sine of x and then plus 4. Now we still need to figure out the value of a. And I'm going to make this a. I'm going to keep this a value red here because why not? Now we have to think how can we determine the value of A? Remember that in order to find the maximum, we go from axis of symmetry A units higher. So we're going to use this fact or this concept. So we're going to say that the value of the maximum is axis of symmetry, and then you add the amplitude. And in this case, we have the value of the maximum, which is a 7. We have the value of C, which is 4. And we need to find what the amplitude is. So plus amplitude. So simply solve the equation for the amplitude. So take 4 to the other side. Oopsie. So take 4 to the other side, and then we figure out here that the value of A will be 7 minus 4, and that would be equal to 3. So if you try to find the value of A using the minimum, that would be a similar process. So the value of the minimum of the function is from the axis of symmetry, we go down by the amplitude. So what that means is that the value of 1 equals axis of symmetry, which is 4, and then minus the amplitude. And if you take this term to the other side of the equation, then you get the amplitude, which is equal to number 4, and then subtract 1. And 4 minus 1 is equal to 3. So as you can see, we end up with the same A value found in two different ways. So one of the equations in this case that we can form is y equals 3. It's a sine function of x and then plus 4. So 3 will be the amplitude and 4 will be the vertical translation. Now, in our case, the period length is 360 degrees, same as the basic function, which means that we have the basic sine function right here. And this will be the equation of the function.